super hard to differentiate, but knowing that it's in the background, it's always in the, every time that there's a selective sweep or range expansion, it's there. You can't get away from it. So.
All right. Thank you so much. All right, so we have one more talk in this session. It's going to be about stepping stones in goal-directed search.
Awesome. Yeah, thank you all for coming. My name is Jackson Dean. I'm from the University of Vermont, the Complex Systems Center. And yeah, today I'll be talking about finding stepping stones in goal-directed search. So a brief outline of what I'm going to be talking about today. I'm going to start with a general introduction and motivation for why you might want to find stepping stones, why it's a difficult problem, why it's an interesting problem. And then I'm going to talk about our methods for finding stepping stones in the domain that we've chosen, talk a little bit about results, and then tie it into the broader field. So starting at the really big picture, I wanted to highlight this incredible ability of biological evolution to find stepping stones towards increasingly complex behavior. And a lot of these stepping stones don't look like the phenotypes that we see later down the evolutionary tree. And there's also examples in technology. For example, it's not clear that electricity and transistors were necessary stepping stones towards computation, artificial intelligence, the internet, et cetera. But in retrospect, we're able to see that. And so that's a really interesting phenomenon, and I think worth studying. And a really awesome and famous example from the world of generative art and evolutionary computation is PickBreeder, which uses a human in the loop. So the way this works is there's a person who's looking at a lot of images. They choose the ones that they find most interesting or most attractive, whatever. And then those are selected, mutated in a traditional kind of evolutionary process. And you end up finding these interesting trajectories of images that include a lot of stepping stones that might be otherwise unintuitive. So for example, if you look at this skull image here on the right, these stepping stones that led to that skull are not necessarily intuitive, but in retrospect, we can see that they did actually lead to that image. So we were interested in trying to find an automated way to identify these stepping stones, a way to say, you know, we want to find the skull image, and then without knowing what these stepping stones were beforehand, how do we evolve an image to look like that in the end? So PickBreeder uses compositional pattern producing networks, or CPPNs, which are artificial neural networks that transform coordinates. They look something like this. So you pass in an X and Y coordinate, for example, you pass it through this artificial neural network, and on the other side, you get the pixel color at that coordinate. And they have a lot of really interesting features for evolutionary computation. Notably, they have unconstrained topology, so you can arrange these nodes and edges in pretty much any way you'd like. They also can have various activation functions on their nodes, which allows for features like symmetry, repetition, variation, other features that are very useful for art, but also in other biology kinds of contexts. And so they're used a lot in evolutionary robotics, generative art, and a lot of other artificial life adjacent fields. And our task, again, was to try and evolve one of these to produce a specific target image. So these CPPNs are often evolved with neuroevolution of augmenting topologies, or NEAT, which has a lot of interesting features. Notably for us, it uses historical markings to track innovations so that it can later use that information for determining parents that might be compatible for crossover. It is able to change both the architecture of a network, the topology of the network, and the weights of the network at the same time. These networks grow from a small network at the beginning to larger networks over time, which is useful for evolution. And then it uses speciation to maintain diversity in the population. So our approach is going to be to incorporate a number of techniques from deep learning into CPPN NEAT to try and find those stepping stones in a PickBreeder kind of setup. So we're going to use backpropagation, Fourier features, perceptual fitness, which are things that I'll define here in a minute. And we're going to demonstrate that even with the increased exploitation from these deep learning techniques, we're still able to maintain diversity and generate hopefully some interesting looking CPPNs. So starting with NEAT as our kind of baseline here, NEAT is able to add and remove connections to a network. It's able to change those activation functions, and then the weights are usually mutated by perturbing them with some kind of random noise. In this case, though, we're going to replace that last step with backpropagation. So we're going to be updating just the weights with backpropagation. And we're not the people to invent this. This is a very well-studied phenomenon that's been used to great success in the past. But again, that's just on the weights, not on the structure of the network. And the intuition for why that might help is that it might actually smooth the fitness landscape for evolution. If we don't have to search for both the structure of the network and the weights of the network with NEAT, we're using backpropagation for the weights. That makes it easier for evolution to hopefully find structures that are useful. Once we start adding these deep learning approaches, we start running into problems that are commonly studied in deep learning. One of them is spectral bias, which is the idea that these types of networks are biased towards low frequency signals. It's much easier to learn a kind of blurry image, for example, in this case, compared to a very highly detailed image, because those lower frequency signals are just more salient to these networks. And that's usually overcome with something called Fourier features. So the idea here is that you take those X and Y coordinates that we're passing into the CPPN and you transform them with the Fourier transform. And that's able to expand the range of frequencies that are available to these networks, resulting in a higher detail image there. So this is what those features actually look like. You can see we have X and Y on the top there. Those are your traditional CPPN features. And then we're using a bunch of random rotations and scalings of Fourier features. And then all of these are passed to the CPPNs, which allows evolution to kind of pick which frequencies are most useful for a given image. Another piece of this puzzle is perceptual similarity. So we're implementing perceptual similarity based on this learned perceptual image patch similarity, or LPIPS. For the sake of time, I won't go into too much detail on it, but these researchers found that traditional sort of pixel matching fitness functions don't align very well with human perception, that they tend to favor kind of blurry images and things like that, whereas deep artificial neural networks are very good at identifying the image that a human would think is perceptually similar to a target image. So this is kind of what our complete inner loop looks like here. We have our inputs. We pass those through the Fourier transform to get our Fourier features. Those go into the CPPN to get our image. And then we compare that image to the target image using our perceptual loss. And the gradient of that error is then backpropagated through the CPPN to update the weights. And then the outer loop looks a lot like NEAT. So we start with our network architectures. We mutate the topology of those networks. And when you do that backpropagation step, then we evaluate and speciate and do the reproduction and crossover the same way that you would do in NEAT. So to kind of briefly summarize that, we're again implementing a lot of deep learning techniques and combining them with CPPN NEAT to hopefully find stepping stones in a pick breeder kind of setup. And I want to emphasize that we're not the first ones to do any of these things individually, but kind of the first ones to put them all together, especially in this kind of evolutionary context. So looking at a little bit of results here. So we're looking at our perceptual fitness for kind of an ablation study. So the blue line there on top is showing that when we have both Fourier features and backpropagation, we get the highest perceptual similarity, followed by just backpropagation without the Fourier features. And both those do better than the classic NEAT. Interestingly, if you just add Fourier features to classic NEAT, you actually do worse than classic NEAT, kind of highlighting this idea that if you have better features that you're inputting to your network, you also need a more robust optimization technique to kind of take advantage of those features. So looking at some of the actual stepping stones that were found here, with classic NEAT, we get very quickly stuck in a local optima. We're trying to replicate a butterfly image here. And you can see that a lot of these, they're not even really stepping stones. They're just kind of stuck in this local optima. Whereas when we have backpropagation, Fourier features, and perceptual similarity, our stepping stones are much more useful towards getting towards our goal. And we do end up with a result that looks quite nice at the end of evolution. So looking at now at species champions, we can see that with mean squared error and classic NEAT, we get these very blurry kind of images. This is what you would expect. Mean squared error is not a very good fitness function for this. And classic NEAT is not able to find great images. But when we switch to perceptual fitness, we're immediately seeing that the images are a little bit more interesting and kind of, again, perceptually similar to the target, not necessarily closer in terms of pixel match, but closer in terms of perceptual similarity. Adding Fourier features increases the detail of these images. So again, these are actually a worse match than the classic NEAT, but they do have higher frequency details, which we can see with sort of some of the detail there. And then adding backpropagation without Fourier features gets, again, closer matches, but we're still not quite there. And we're seeing a lot of, we're lacking detail without those Fourier features in a lot of cases. Now, if we add backpropagation and Fourier features, but don't use perceptual similarity, this is where we get a lot of blurry images that have all the right colors and gradients, but are missing a lot of the detail and the correct shapes. And then finally, if we have backpropagation Fourier features and perceptual similarity, so kind of all of our proposed methods here, that's where we're getting not only the closest matches, but also, in my opinion, kind of the most interesting matches. Yeah, again, combining all those features to get a nice result there. And then you might expect that adding these kind of exploitative deep learning techniques would actually reduce the diversity of the population. But we actually find that to not be the case, that actually when you have backpropagation, you actually get higher diversity. And we suspect that this is because the backpropagation is enabling evolution to search more effectively in the architecture space, that if you make a large change to a network and then find weights that work well for it, that kind of enables you to explore a little bit better because you're not having to simultaneously find good weights and good topology in the same step. So looking at kind of phenotypic diversity here with classic NEAT and LPIPs, we're seeing that there is quite a bit of diversity here, but it's not very interesting diversity. We're getting a lot of solid colors and simple shapes. Switching to Fourier features, backpropagation, and not perceptual fitness, but mean squared error. We again are getting a lot of blurry stuff. We're still seeing a lot of phenotypic variation, but again, it's not what I would consider interesting phenotypic variation. And then finally, with our proposed changes here, Fourier features, backpropagation, and perceptual similarity, we're seeing the most interesting visual diversity. And I think it's very interesting here that a lot of the features are actually canalized in the population. For example, we're seeing that the structure of the butterfly, the shape of the butterfly is very consistent here, but the patterns and colors are varying, which is not only visually interesting, but also very useful for evolution to find nice solutions. So in conclusion, we use a lot of deep learning techniques here to add to CPPN NEAT, and we found that they harmonized well with the evolutionary approach. And so we were able to find stepping stones in a very difficult fitness landscape. We saw that backpropagation actually enabled a wider range of mutations to be useful, so actually increased the diversity during search. And then we still saw that phenotypic variation despite having the extra exploitation. Fourier features, again, increased the detail of the images. Perceptual similarity seemed to work well, and we found those stepping stones in this difficult fitness landscape. So there's a number of limitations and work that we'd like to do in the future. Notably, we only tested one single task. So we just tested an image replication task. This technique is relatively broad and could be applied to any number of problems, but we only tested the one here. We also only tested LPIPs as an objective function, but there's a number of other perceptual similarity or just other objective functions that would be interesting to look at. We also got images that were pretty good, but again, not exactly right. So there's still a long way to go in terms of image replication with CPPNs. And then we tested this approach without SGD, but we didn't actually test it without NEAT. So it's unclear how much of the sort of benefit is just provided by SGD and what the actual synergy is between backpropagation and NEAT in this case. And then also we were very inspired by open-ended work, but this itself is not an open-ended problem at all. We kind of did a very goal-directed version of this, but we think a lot of these techniques actually would apply to a more open-ended approach, especially in terms of feature augmentation and potentially even backpropagation if it was implemented correctly. And then we're also very interested in multi-objective evolution. So we have some work coming out soon that's going to be a more multi-objective approach to this. So instead of just using perceptual similarity, using a wider range of fitness functions. And we see that actually works quite well. So I actually have an example of that here. So you can see this is from our work, multi-objective optimization via voting for elites or MOVE, where we're getting even better results by combining a number of fitness functions altogether. So awesome. That's all I have. Thanks for your time, and I'm happy to take any questions.